Okay, we are going to start. Quick recap of what we did last class. Okay, so the basic thing that we saw was this idea of an NK code. Okay, so the NK code is nothing but a k dimensional subspace of F2n. Okay, remember what is F2n? F2n is the set of all n length binary vectors. You have a vector space when you define a vector space with them with modulo 2 operations. Okay, so it's a vector space over the scalars over the binary field, okay, 0 1. All right, so that's the basic idea, and the usual way to specify this k dimensional subspace is to specify a generator matrix. Okay, which is k cross n. Oops, that became a ugly looking matrix, but yes, that's better. So it's a k cross n matrix. The first row, second row, etc. specify the basis for the NK code. Okay, so basically you specify a matrix and say the code, the NK code is the row space of G. Okay, so clearly I am thinking of a rank k matrix. Okay, so that's another thing which is important. Rank equals k. All right, so this is pretty much all that we saw, and the next thing we saw was to basically do Gaussian elimination on this matrix and convert it into what I call the systematic form. Okay, so you can do Gaussian elimination and convert it into a form which looks like this: ik and then a parity part p. Okay, remember what are the steps that are allowed in this Gaussian elimination? You can do row operations, which is basically row swaps and row additions, and then column swaps are also allowed. Okay, only then I will get ikp. If you don't allow for column swaps, what will happen is the columns of ik might be spread over the entire matrix. It will look a little uglier, that's all. Okay, so if you do a simple row column permutation, you get back to the original matrix. Okay, so remember the row space will be altered when you do column swaps. Okay, only if you assume that permutations are okay, it is the same code. Okay, if you want to retain the same row space, you should not do column swaps. Okay, you should live with an uglier looking G which has the columns of I spread out over the entire matrix. Okay, so row operations are performed. Okay, I'll put column swaps in bracket. Okay, a good linear algebra question at this point, just to test your background a little bit, is under what conditions will you not need a column swap? Under what conditions on this generator matrix G?
IKP.
Okay, so think about it. Okay, so when you do Gaussian elimination, you will have to find the pivots just with row swaps and just row swaps. Okay, so you will not need any column swaps when you do the pivots. Okay, it's not a difficult condition to think about, but essentially one of the necessary conditions for that to happen is the first k columns of G should be also linearly independent. So you should get an invertible matrix. That's a necessary condition. On top of that, you also need the pivots to come one after the other nicely. Okay, only then you will get it. Okay, all right. So that's the recap, and now we are going to move on with the next way of viewing the same code. Okay, so this NK code, this is the normal basis view. Then there is also the dual view. Okay, so I was giving a brief motivation in the last class of how you can think of the 3D space. You define a plane either by specifying two linearly independent vectors on the plane, or you define one vector which is normal to the plane. Okay, so you either define the dual or the original space itself. Okay, so here also we can do something similar. I am going to motivate it using a simple example, and then I will tell you that this is in general true. Okay, so let's see that. Okay, so here's an example to show you how the dual space comes about. The example for dual. Okay. Remember our first example was this 6.3 code, right? How did I define the 6.3 encoder? You remember I had a very simple example where I had a code where let us say the 3-bit message going in M1, M2, M3 gets encoded and what comes out is M1, M2, M3 and then M1 plus M2, M2 plus M3, M1 plus M3. Is that right? I had the code like this. Okay. So, now if I basically this is a code word, right. So, I could denote it as C1, C2, C3, C4, C5, C6. Okay. Alright. So, every code word of this code is formed in this way. Okay. So, basically I have 6 equations which tell me what the code word is. Okay. What are those 6 equations? C1 equals M1, C2 equals M2, C3 equals M3 and what is C4? M1 plus M2 and C5 is M2 plus M3 and C6 is M1 plus M3. So, the first 3 equations are not really anything that you can control, that is just free equations, right. You can pick any value you want for M1, M2 and M3. So, likewise for C1, C2 and C3 you can pick any 3 bits that you want, okay. And then C4, C5 and C6 get fixed in terms of the first 3 bits, okay. So, let me write that down a little bit differently. So, I have 3 equations which tell me how the parity bits are computed. C4 equals C1 plus C2, C5 equals C2 plus C3, C6 equals C1 plus C3, okay. So, one thing I can do now is to write these equations which we are seeing as operations to get the parity bit as a condition on the bits of a code word. Okay, so, what will I do? I will move the things on the right hand side to the left hand side. Okay, so, equivalently I have these 3 equations C1 plus C2 plus C4 equals 0. Okay. It's good that you asked me minus, but minus does not matter. So, remember whenever I write plus pretty much throughout this course it will be modulo 2, okay, except if I am dealing with real numbers where it obviously will not be modulo 2, it will be always modulo 2. Okay. So, I know I have to write C4 minus C1 minus C2 equals 0, but minus 1 is the same as plus 1 in my field, okay, 0 1 that I am dealing with. So, it is just plus, okay, it is just binary XOR, okay, that is the way to think about it. C2 plus C3 plus C5 equals 0, C1 plus C3 plus C6 equals 0. Okay. All right. So, these are a different way of describing the encoding operation. Okay. So, you can see you can go from the encoding operation to these 3 conditions. You can also do the reverse. It is not too hard to see that you can do the reverse. If I give you only these 3 conditions, from here you can go to the encoder also. How will you do it? You have to stare at it for a while, or there is another way of doing it which is also equally the same, but you stare at it for a while and then you realize C4, C5 and C6 can be thought of as dependent variables and C1, C2, C3 can be thought of as independent variables. So, you pick the independent variables any which way you want and pick C4, C5, C6 as dependent, you will get all the solutions. There cannot be any other solution. Okay. So, the same code I can describe in 2 different ways now. What is the first description? I described the code word as a message times a generator matrix which looked like this, right, I and then a P, right. Now, I am getting a different description which I can loosely term as the dual description. I will tell you why it is the dual description. A code word has to satisfy, every code word has to satisfy these 3 conditions. Okay. What are the 3 conditions? They are written down here. I can write them also in a matrix form. Okay. So, let me write that out for you, you will see how it works out. Okay. I want to have a matrix here and then I want to put C1, C2, C3, C4, C5, C6 here and what do I want on the right hand side? I want 3 zeros. Okay. The question is, what should I put in this matrix? Okay. So, it is just, it should codify these equations, it is not too difficult to see once you know how matrix multiplication occurs. It is simply 1 1 0 1 0 0 0 1 1 0 1 0 1 0 1 0 0 1. Okay. Okay. So, I did not really prove it but from the way I did it, it is quite clear that both these descriptions are perfectly equivalent. Okay. How do I find the code words? I could find the code words by writing them down as m times this matrix and going through all the different possibilities for m. How many different possibilities will I get? 2 power 3, which is 8 possibilities. I will get all the code words, I will get 8 different code words. Okay. Or I could look at this set of equations, which is a little bit different. You can't immediately create the code words from it, but a minute's thought will tell you how to create the code words. Okay. So, you look at the matrix a little bit, you can do that, but this is also equivalent. If I ask the question, in the set of all 6-bit vectors, give me all those vectors which satisfy these 3 conditions written down here. Okay. Right, these 3 conditions written down here, give me the set of all 6-bit vectors which satisfy these 3 conditions. Guess what I will get? I will get the exact same code words that I got before. Okay. There will be only 8 of them and you can enumerate them. Okay. So, how do you do it in this particular case? Like I said, I mean, you will have to stare at it for a while and realize that C1, C2, C3 are independent variables, C4, C5, C6 are dependent variables. You vary them a lot, you get it. Okay. So, the description on the left is the basis description and the description on the right is the dual description. You can see why it is a dual description. I have given you a matrix on the left hand side whose row space is the code. On the right hand side, okay, also there is a matrix. Okay. How is the code related to that matrix? Okay. So, there is a name for that space. Okay. So, you have the row space, which is all linear combinations of the rows. What is the space on the right hand side now? It is the null space. Okay. Set of all vectors, so that this matrix times that vector equals 0. Okay. So, that is the null space. Okay. On the left hand side I have the row space description, on the right hand side I have the null space description. Of course, the matrices are different, okay, but clearly like I derived right now, one can be derived from the other. Okay. So, we will see a general way of doing it also. Okay. So, this is the motivation or the general basic idea behind the dual description. This can be extended in general also. Okay. So, which we will do immediately. Okay. If there are any questions, quick questions on this, now is a good time to ask. Okay. All right. So, let me do the dual code and parity check matrix. So, that is the title for what we are going to see next. Okay, it might actually be parity check matrix and dual code. If I might do either way. So, that is what we are going to see next. Okay. So, let me start with an NK code. With generator matrix G, which is in systematic form. Okay. So, like I said, I mean any generator matrix that you have can be put into this form with enough column swaps. Okay. So, in case you cannot do it, if it is not given in systematic form, you do a series of Gaussian elimination steps, get it to systematic form. So, we can assume it this way. Okay. It is not a big problem. So, this is where we start with. Okay. So, let us say this code is called C. Okay. C is an NK code with generator matrix G. Okay. So, how do I think of a code word of C? Okay. Any code word of C is computed by MG. Okay. Code word MG, which is m times I k p. Is that right? Okay, so now just repeat the same steps that I had before. Okay, so if the code word is C1, C2, so on through Ck, then Ck plus 1, Cn, I know this will be equal to what? M1 through Mk, and then I will write it as m times p. Is that okay? Okay, I know this is, I mean, if you have enough experience with MATLAB, this kind of notation will be easy to you. Okay, it's like all MATLAB notation concatenations. Okay, when I write MP, it means you get a parity vector which has to go there and fill out the whole vector. Okay, so now this guy is the message part, this is the parity part, all that is known. Okay, so now what should I do? What should be the next step? Okay, and then yeah, move it to some side and then do the idea, right? So that's a similar step to what I had before. Okay, but let me write it down a little bit differently, see how it works out. Okay, so the same thing I'm going to write down a little bit differently in a column vector form. Okay, so it might be a bit more difficult for you to see, but hopefully it's clear enough. Okay, so the same as before, but I'm doing it a little bit differently. Okay, I'm going to write this as, how should I write it? Okay, so I have to do a transpose, right? So because MP is a row vector, I want a column vector, so I should do MP whole transpose, which is the same as P transpose M on the right. Okay, so what is M? M, if I transpose it, I simply get C1 through Ck. Okay, so stare at it for a while and convince yourself it's the exact same thing. Okay, so I've just written it in a little bit different form. Right? I'm writing Ck plus 1 through Cn equals MP. I'm taking transpose just to get the same format as before. Is that okay? All right. So now what do we do? What was done in the next step? I have to Ck plus 1 through Cn. I should move to the other side. Okay, so how will I do that? I can take it to the other side and equate to 0. Then what should I do? Okay, I want to write one matrix times the entire vector. Okay, so all that I will do in one step in the next slide, but hopefully it will be clear to you. Okay, so I'm going to move to the next slide and just do everything in one step. Okay, so you will basically get P transpose I n minus k multiplying C1 through Ck and then Ck plus 1 through Cn, and what should come on the right hand side? 0. Okay. So this is the same as what we had before, except that I have written everything in a convenient single matrix form. The same thing, I moved everything to one side and I wrote it. Okay, so if you want to parse this, P transpose times C1 through Ck plus I times Ck plus 1 through Cn. Okay, I times Ck plus 1 through Cn is simply the column vector I. Okay, so just you get the exact same thing. Okay. So one more thing to really check real quick is this, is the dimension. What is the dimension for P? K by n minus k. What is the dimensions for P transpose? N minus k by k, and then you have an n minus k here, remember that. Okay, so you get the same n columns as before. Okay, so how many zeros will be here? Okay, n minus k zeros. Is that okay? Okay, so this matrix is called the parity check matrix. usually it is denoted H. Okay, the generator matrix is usually denoted G, the parity check matrix is usually denoted H. And you see there is a very simple relationship between G and H if you have it in systematic form. Okay, so if G is given in systematic form as IK P, then what happens to H? H is P transpose I n minus k. Okay. All right. The code now has two different descriptions, set of all code words such that C equals m times G, m belonging to F2k, which is also given as set of all C such that H C transpose equals 0 C belonging to F2 n. Okay. And we saw it quite easily that these two are the exact same descriptions for the exact same code. Okay, and if you have it in systematic form, it's very easy to write down. Okay, one is the basis description, the other is the dual description. Okay. Okay, so we already saw an example, so I am not going to give another example. Okay, for the 6.3 code we saw an example, you can also see other more crazy examples. So let me give you one more example which is maybe a little bit more crazy. Okay, so you might think will get you thinking. Okay, so let's say G is 0 1 0 1. Okay. All right, so it's a bit of a simple looking generator matrix. Okay, so what will happen if you form H from it? Yeah, we'll get the exact same matrix. Okay, so something strange. Okay, so something like this can never happen in the real space. Okay, if you look at R4, if you want to describe a two-dimensional subspace of R4, you can describe two basis vectors, but the same basis vectors can never describe the dual space, right. So, the dual and the regular subspace will not intersect at all, they will intersect only in at 0. Okay, so, here you have the strange case where both are the same. Okay, so, I will tell you why this happens. Okay, so, you will see there are a lot of reasons why this happens, but it is a bit of a strange thing to keep in mind. Okay. All right, so let us now define the dual and then connect it with the parity check matrix. Okay, so, it is not too difficult. Okay, so, we will do that first. Okay, so, suppose I have an NK code C, the dual is defined as follows. C perp is, it is denoted C perp, dual of C, okay, denoted C perp, it is the set of all C such that C U transpose equals 0 for all U in C. Okay. So, you see already there is some minor inconsistency in my notation, with some vectors I am putting a bar below and some vector I am not putting a bar below. Usually I will put a bar if there is some confusion of using small c and capital C. Okay. So, just to remind yourself that small c is the code word and capital C is the code itself, okay, which is a set of all code words. Okay, so, usually there will not be confusion, but sometimes if I do not write the capital C really big, you might get confused. So that is why I put the bar below. Okay. So what is the CU transpose? This is basically C1 U1 plus C2 U2 plus so on till Cn Un. Remember everything is modulo 2, okay. So I never wrote modulo 2 here, but it is clearly modulo 2, okay. Any matrix multiplication I am doing with binary vectors and binary matrices is modulo 2, it is always assumed to be modulo 2, okay, alright. So this is defined as the dual, okay. On first glance it looks like maybe there is no connection with the parity check matrix, okay. So but there is some connection. What is the connection that you can maybe see real quick? Yeah, I mean so words you can see many connections, but in terms of equations you see that CU transpose equals 0 is giving you some hint, okay. So H times C transpose is 0 for every code word in the code, okay. So something that we can identify from this is very important, okay. Yeah, so we will come to that soon enough, but before that we have to first see what is this dual, okay. So we will try and prove some abstract properties for the dual and then quickly see what is it actually, okay. So you will see the dual ultimately will become the row space of H, okay. So you can imagine that this has to happen, I mean that is how the definitions work, but I mean this is quite clear from linear algebra, but I want to develop this a little bit more slowly so that the impact of this is you get the impact of this. This is quite important. The dual code is very important. Many of the decoding algorithms work with the dual code, okay. So it's a very important idea to get your head across, okay. Alright, so this we will get to this eventually, but let us see how this works out, okay. So the first claim I want to make, the first property that we will show is that C perp is a subspace of what? F2n, okay. I won't rigorously prove this, but I will simply tell you what the proof is, it is not too difficult, okay. So what is a subspace of a vector space? What conditions create a subspace? Any two vectors in the space, when you do linear combinations with them, you should be in the same subspace, okay. What are the linear combinations? You take a vector and multiply it with a scalar, okay. So for us the scalar is really nothing, 0 or 1, so it will be trivially satisfied, no problem. But when you add two vectors, I should get another vector in the same space. Can you prove that with this definition? Okay, so if I take a C1 which satisfies this condition and take a C2 which satisfies this condition, C1 plus C2 will also satisfy this condition, okay. So it is a very easy thing to show, okay. So we are able to show C perp is the subspace of F2n, okay. The next thing is with the dimension and a basis, okay. So I know C perp is a subspace, I know C, okay. C is an NK code which is clearly a subspace, okay, and I have a nice description of it. Maybe I have the generator matrix, okay. So maybe I should include that, say with generator matrix G, okay. So that is the definition for the NK code. Now I might want to find the generator matrix for C perp, okay. Then that completes my description of C perp, okay. So I am able to quickly see it is a subspace, there is no problem with that. Then how can I find the generator matrix, okay. So now I am going to invoke some basic ideas from linear algebra and quickly get to the result, okay. So without too much of worry, okay. So the first thing we know is C is the row space of G, okay, alright. We know that, do we know that or not, okay, right. So that we know. So essentially I am looking for what? If you think about the dual in terms of the row space, column space, etc., okay. We also have another description of C which is the in which case it becomes the null space of H, okay, which is some other matrix, right. So it seems like a slightly different definition. Now suppose I ask you for the null space of G, Okay, what will be the null space of G? Okay, so let's look at this a little bit more clearly. Okay, so G is your basis. Okay, so let's say ik and p. Okay, so H is going to be a very simple relationship again, P transpose I n minus k. I have C described in this form. Okay, so notice what is C perp? C perp is set of all vectors in F2n which are orthogonal to all vectors in C. Okay, so remember, if I want something to be orthogonal to all the vectors in C, it is enough if it is orthogonal to the basis vectors of C. Okay, so that is the first idea from linear algebra that we will use. Okay, C perp, I defined it as set of all vectors which are orthogonal to every vector in C. Okay, so equivalently it simply becomes set of all C such that, okay, C times G I transpose equals 0, where what is G I? Okay, so rows of the generator matrix. Okay, so G I, remember, is the ith row of G. Okay, so this condition I can write it slightly differently, which will clearly tell you where the definition comes from. G times C transpose is 0. Is that okay? It is just the same thing. I mean, C times G I transpose is 0. You transpose that, what do you get? G I times C transpose is 0, and this is true for every row. You just put it all together into a matrix equation, you get the answer. Okay, all right. These are all completely equivalent ideas. This comes because orthogonality with all vectors in the code is the same as orthogonality with the basis vectors. Okay, so once I do that, I am done. There is no more problems. Okay, now the answer just falls out of the equation. Okay, right. If I look at G and think of G as the parity check matrix of some code, what will that code be? It will be C perp. Okay, so that is the idea. All right, so that just immediately gives you the answer. Okay, so C perp will be null space of G, which you can show will be the same as row space of H also. Okay, so I have not proved this, but it will be the same as that. Okay. Okay, so the first part we have proved, the second part I have put in brackets because we did not necessarily prove it, but it is kind of clear if you know enough linear algebra, it will be reasonably clear to you. Maybe we will prove it soon enough. Is there a question? No question? I want to ask it in public? No? Okay. So hopefully this simple derivation is clear. I mean, there is nothing much in this, but first time you see it, it might be a little bit confusing. It's too many spaces floating around. Okay, all right. Okay, so let's do a little bit more of quick computations with C perp. So remember, H has dimension n minus k cross n, G has dimension k cross n. Okay, and C became an nk code. Okay, G is the parity check matrix for C perp, and its dimension is what? K cross n. So what kind of code will C perp be? N comma n minus k code. Okay, so all these are kind of interesting and obvious properties, but it's good to know that. Is that okay? It's clear just by looking at these dimensions. If you have a parity check matrix for a code C, it's going to have dimension n minus k cross n. Okay, of course all these full rank assumptions are already I've already made it, otherwise you won't get this answer. So, we have n minus k. Now, C perp becomes null space of G, which means G is the parity check matrix for C perp, and just by looking at the equations you see C perp is an n minus k code. Okay. So, now how do I quickly see that the null space of G and the row space of H have to be the same? Okay. You can go through the same operation as we did before. Okay. So, you start with the null space of G, define a code, and then do the left to right switch with the I and P, you will get back your H. Okay. So, we did from C equals mg, we went to H C transpose equals 0. Now, you start with G C transpose equals 0 and you redo the same thing and go to some C equals m H. Okay. So, you will get that same thing. Okay. If you want I can do that again. So, let me quickly do that, it is not a big deal. Okay. So, what do we have? I thought I had a 50-minute clock, is it gone? So, how do I, okay, I will go on, just give me a warning when 50 minutes are up. Okay. All right. So, okay, so let us see that. So, right now I have the dual code described as the null space of G, which is what, I k p times C transpose is 0, right. This is the equation that I have. Okay. So, what should I do now? It's a little bit more interesting to ask this question this way, right. Okay. So, let us see. So, write it down differently, write it as C1, C2 so on till Ck plus P times Ck plus 1 all the way down to Cn equals 0. I will put a 0 with a bar below and you have to put as many zeros as you need. Okay. So, now this is the same as what, C1 through Ck equals P times Ck plus 1. I know enough of you are saying minus, but it is the same as plus. Okay. So, it goes to the other side without any sign change. Okay. That is a nice thing about dealing with binary arithmetic, right. So, you have this. So, now which is the independent variable and which is the dependent variable? C1 through Ck are dependent variables. Okay. So, remember your m should be Ck plus 1 through Cn. Okay. So, the role of the parity and the message gets switched in this role. So, you have to think of this as your message m. These are the independent variables. Okay. So, if I do that I can write C as m times what, P transpose and I. What is this I now? I n minus k, and remember m is an n minus k bit vector. Is that okay? All right. So, I simply get the same thing as before, which is m times h. Okay. So, my C perp, which started as null space of G, became the row space of H. Okay. So, all these things are very obvious if your linear algebra is very fresh in your mind, but even if it is not, I think this derivation should convince you that it is the same. Okay. So, these are just quick and dirty derivations using the systematic form. If I do not use the systematic form, the notation becomes a bit more messy, but you get the exact same answers. Okay. So, I will not be there, it will be somewhere else. You have to collect the different columns and put the P in different places, you will get the same answer. Okay. So, that is the idea. All right. So, let me go back to the previous slide, hopefully this derivation is clear. So, this is what is very important. So, now I can erase the bracket because I have clearly proven that to you. Okay. And now it is all the more clear why C perp is an n comma n minus k code. Okay. So, it is the row space of H, it has got n minus k vectors, it's clearly n minus k rows which are linearly independent, and you get n minus k. okay, all right. So what is the summary now? Okay, so you have C being an NK code generator G parity check. I will use PC for parity check matrix H. Okay. Okay. Now C perp is what? It is an n comma n minus k code. What is the relationship between C and C perp? Yeah, you take a vector in C, it is going to be orthogonal to all the vectors in C perp. Okay. And you take any vector in C perp, it is going to be orthogonal to all the vectors in C. Okay. And you have to do a switch here. What is the generator for is H and the parity check is G. Okay, simply do a switch. All right. So this duality or orthogonality is with respect to the inner product, the usual inner product, except that you have to do modulo 2. Okay, so that is the inner product involved in this duality is basically if you have two vectors x comma y in F2n, x dot y is basically x y transpose, okay, which is basically x1 y1 plus x2 y2 plus so on till xn yn modulo 2. Okay, so this duality is with respect to this inner product. Okay, so that is what I mean when I say orthogonal. Take a vector in C, vector in C perp, do this operation, you will get 0. Okay. So this inner product is not as nice as the Euclidean inner product in Rn and all that. Okay. For instance, you know that x dot y, x dot x for instance can never be 0 in the Euclidean inner product, but x dot x can be very easily be made 0 in this even if x is not 0. Okay. Right. If you have any x which has an even number of 1s, if you do x dot x you are going to get 0. Okay. So a vector can be orthogonal to itself, which is a very strange idea in Euclidean space. So that is why you get such examples. I had an example for you, right. C and C perp were exactly the same. Okay. You can have C equals C perp. Okay. That is because the same vector can be orthogonal to itself. Okay. So that is the bit of a counterintuitive idea about this binary vector spaces. Okay. So these are finite vector spaces over finite fields, and some strange things happen with the regular inner products that you are used to. Okay. The modulo 2 is not a very nice inner product that way. Okay. All right. So that is with the dual. So let us see a little bit more of a complicated example and see some nice in the last 4 minutes that I have. So let me do let me take a generator matrix, or let me take a parity check matrix. I am sorry. Okay. Okay, so this is the parity check matrix. This happens to be a parity check matrix of a very famous code, which is the 7-4 Hamming code. Okay, and okay, first of all, how do I know that this is a parity check matrix for a 7-4 code? Okay, so that is the first question. Given a parity check matrix, you have to find out the dimensions, the n and k for the code. Okay, so n equals 7. That's just basic counting. Okay, so it's the number of columns 7. What about k? Okay, so you have to see n minus k, and how do you find n minus k? It equals to the rank of the matrix H. In this case, the rank is obviously 3. How do we quickly say that the rank is 3? Yeah, first, second and the fourth column are clearly linearly independent, and just that becomes the rank, and that is 3. Okay. So rank cannot be greater than 3, no? It's clear, right? So it has to be either the minimum of lesser than the minimum of the one. So n minus k equals 3, n is 7, which implies k is 4. Okay, so this implies k is 4. Okay, so the rank computation is important. I am not even writing it down, but hopefully it is clear to you. Okay, why does this matrix have full rank? Okay, rank equals 3 because the first, second, and the fourth column are linearly independent. Okay, so because they are 0 0 1, 0 1 0, and 1 0 0. Okay, so now you have to go through your Gaussian elimination and find the parity check, the generator matrix corresponding to this. Okay, so that might be a good exercise to try, but it is easy to do a row column swap first, apply your formula, and then undo the column swap to get a valid generator matrix. Okay, so it's good to, when you deal with row spaces and null spaces, it's good not to do column swaps. Okay, but then if you don't do column swap, the IP formula will not apply. Okay, and then you will get confused. Okay, so the best thing to do is do the column swap, but keep a record of it. Okay, know which columns you have swapped. Okay, after you do the IP and then you do the P transpose I, what do? You undo the column swap, then you don't have to do any permutation. It's the exact same match. Okay, so the first step I have to do is a column swap here. Okay, I'll swap these two columns and then I'll rearrange the rows so that I get it into the form IP. Okay, which is not the standard form for the parity check matrix. We've always thought of it as PI, but it doesn't matter. I mean, the same formula will hold whether it is IP or PI. You just have to put the P transpose in the right location. Okay, so I do the column swap and then I rearrange the rows. Okay, so I get an equivalent form which looks like this. Okay, 1 0 0 1 0 1 0 1 0 0 0 1. Okay, okay, 1 1 0 1. I'm sorry, 1 0 1 1 and then 1 1, no, 0 1 1 1, right? Is that okay? So that is the form I get. So this is my I3 and this is some P. Okay, so how do I get a G corresponding to this? I have to do a P transpose and an I4. Okay, so you do a P transpose, you get 1 1 0 1 1 0 1 1, and remember my third and fourth column got swapped. Okay, so I should put the I here and then 0 1 1 1 here. Okay, and then I would get the exact same. Okay, so this is nothing but a P transpose I with this swap. Is that okay? So now, so you might still wonder if I did all the swapping and the operations correctly. Okay, so there's a quick way of checking. What's the quick way of checking? Yeah, so each row of H has to be orthogonal to each row of G. Okay, and that is actually a necessary and sufficient condition. It's enough if you check for those two. Okay, right? I know that the row space of H and the row space of G are orthogonal, but to check if the row spaces are orthogonal, how can I check? You can simply check the rows. It's enough. The bases are orthogonal implies everything is orthogonal. Okay, so that you can check. Essentially, you can check G H transpose equals 0. Okay, so you can check that. That will be a valid condition. Okay, so let's stop here for this lecture and take a break. We'll come back and do the next lecture. So